では先にご紹介しますね。演題がですね、カリプトラおよびオープンタイタンチュートリアルということでですね、須崎先生ご説明いただいた、オープンルートオブトラストファームウェアのアーキテクチャと統合と、Google およびマイクロソフトにおける最新動向ということで、アンドレス・ラガル・カビアさん、特別首席エンジニア Google ということで、ご講演いただきます。Presentation title is Caliptra and OpenTitan Tutorial, Architecture and Integration of Open Root of Trust Firmware led by Google and Microsoft by Dr. Andrés Lagar-Cavilla, distinguished engineer from Google LLC. So please start the presentation. Yeah.
Here we go. Thank you for the introduction. Thanks everybody for waiting. Just to mirror from the menu. 1 second. Okay, we're here. Thank you. A lot of preparation for this presentation, and it's the one before lunch, so let's try to move relatively quickly. I think I will cover some of the things that the prior speaker talked about, so apologies if it's repetitive. I want to talk a little bit about what we do in security using open source, using open source silicon, and using RISC-V, right? So we'll talk about that. We'll talk about two different but very tightly wound together projects called Caliptra and OpenTitan, and I want to talk about the role of RISC-V. So let's start with the basics. Why do we do open source, right? And this is probably something that the whole audience is aligned with. We're looking for high quality peer-reviewed implementations, right? We don't really like security through obscurity, so we're looking for things that we understand, that we can review, that we can change, that we can improve, and that we can build a community that all can collaborate to get the best content in there. And we believe this creates a baseline implementation so that many other companies can deliver very similar products and stay to the same high bar of quality. Open source is a proven method of delivering software. Linux doesn't need any introduction. You know, everybody knows it has worked very well. It's a testament to the philosophy. But for example, you can think of some software projects like OpenSSL as excellent open source implementation of security standards. One of the things we say a lot, or that cryptographers say a lot, is don't implement your own cryptographic algorithm. Just take a library that is implemented by people who know what they're doing. And that would be, for example, in the open source world, that would be the OpenSSL folks. So our goals are high quality implementations. Our goals, there's this refrain, a rising tide lifts all boats, right? The rising tide is the implementation with high quality that can allow the entire community to bring the same level of security. And of course, security through transparency. Now, we talk a lot about software. Why does silicon security matter? I mean, software is loaded by software, right? Maybe here I'm repeating some of the things from the prior presentation, but you know, you have an application, it's loaded by a kernel, the kernel may be inside a virtual machine that is loaded by a hypervisor, the hypervisor is loaded by trusted firmware if you're in an ARM CPU, like the prior presentation may talked about, and trust zone firmware is itself loaded by a root of trust inside the chip. Eventually, this is like the refrain turtles all the way down, but at the bottom of it, you have the actual silicon. You have the immutable properties of ROM, a read-only mask, and its code, and fuses, and those mechanisms. So the entire building is anchored to the trust that the bottom of the stack provides in silicon. Now, the challenge, of course, is that silicon is not software. There are limits to the open source silicon journey, and we need to keep on pushing this boundary. So we're going to talk about it during the presentation. I'm going to do a few callouts, Think of it as a little bit of a call to action about the areas where it's not as nice or rosy as in other software environments. So how do we look at this problem, right? I work in AI and infrastructure. I work in data centers, right? So I work in hardware, security of all of that, security of the hardware, right? So you have the big data center, you have the racks, and then you have the machines, machines with TPUs or whatever, GPUs, etc. These are very, very complicated platforms. Any of these machines carries 5 to 8 very large SoCs and probably 25 or more independent CPUs. So you need to make sense of it all together. This is something we presented with a number of other companies that work with us at Open Compute Platform. How do you make sense of the whole platform? You use internal roots of trust in each individual system on chip for attestation. This was discussed in the prior one. We use a BMC to push firmware to all these internal roots of trust. We call this flashless boot. We use sidebands. These are very simple. These are not high-speed paths like PCIe or NVLink, but there are paths like I3C or USB, which are used for control and to harvest attestations and to push firmware. And we try to gather the state of the whole platform, look at each individual chip, look at their public identities, look at the attestation of the firmware that they have loaded, and send it to a trusted verifier. So all of this is nice. This is abstract. The way it looks at Google, and the reason why we're going to talk about OpenTitan and Caliptra, sorry about this, I did this with an LLM and it got a little out of control, as you can see. But we use OpenTitan and Caliptra for those roles, right? We use Caliptra as the internal root of trust on each individual SoC that we have that generates identity and harvests attestation. And we use OpenTitan both as a TPM attached to CPUs for secret sealing and as a platform root of trust attached to the BMC for system recoverability. So I wanted to introduce, you have a big machine, it has a lot of parts, and this root of trusts, both of them, Caliptra and OpenTitan, they have very specific roles. So now we're going to talk about them, about those roles, right? So Caliptra is internal root of trust. It's in each individual SoC. It's a block. You add it to your SoC. It's not a separate chip. It secure boots the SoC, and it cryptographically measures all the firmware. It gives it a unique cryptographic identity, and it's evolving to empower SoCs with key management where needed. And OpenTitan is a standalone chip. It's here later in the demo. We're going to show it. The demo is very simple. It's like a 10-second demo. Here's a chip. But it has its own internal flash storage, so it can seal secrets, it can forget about them, it can do cryptographic agility and rotations. And it can be used as a TPM, but it can also act as the root of recovery, right? In the whole platform, the first thing that boots can be an OpenTitan, and it can itself control the second thing that boots, and so on. So both are open source, and this is a deliberate and intentional thing that we've done at Google. Why? Because we want to trust the implementation much more than the standard. We have a lot of suppliers, there's a lot of standards out there, and we have a lot of difficulty. I don't want to say difficulty. We spend a lot of time and effort in taking each of these implementations that technically conform to a standard, but integrating all the nitty-gritty and differences that they have. So instead, what we were thinking of doing is, hey, here's an open source implementation. If you have a problem with it, fix it, but please use it. And then it's going to be so much simpler to integrate everywhere else with low repetitive effort. And to coalesce a community of integrators, right? As more and more people work on this, they get better, and we all speak the same language. So let's start with Caliptra, right? So Caliptra is a more recent one. We'll talk about how it came to be later. This is the diagram we always use when we talk about Caliptra, right? So you have an SoC, it's a big chip, it's a fantastic GPU or whatever, or an AMD Venice or whatever it is, and there's a quarter of a square millimeter inside of it that is Caliptra, and it's the root of trust, and it carries a couple of critical tasks. It's the first thing out of reset in the SoC. It reads the fuses. It forms the unique chip identity. It loads and measures firmware iteratively. It creates a DICE context. So DICE is Device Identity Composable Engine. It's basically, think of it as, every piece of firmware that I measure, I extend the hash chain and I create new certificates. So it gives me the personality of the chip. It gives me the identity, both the unique identity this chip is 1, 2, 3, 4, 5, and it's not the same as the other one, but also modified by the firmware that has been loaded. That's a very powerful property. We want to know where our chips are and what software has been loaded on it. Alternatively, it has PCRs. PCRs are the control registers from TPM, so you can also extend them. And it generates X509 certificates, so you can query it and you can get a remote attestation, and that remote attestation carries public keys and carries certificates. And now you know everything about the chip. You know what it is, you know that it's genuine, and you know that it loaded the firmware that hopefully you were expecting it to load. So what Caliptra allows every individual SoC in a very complicated platform with 8 GPUs and PCIe switches and 4 smart NICs and blah 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 blah. It allows every SoC to anchor trust independently, to form its own identity, to generate its own cryptographic attestation of itself and the firmware. And once all of that is done, it allows application cores to come out of reset. And those cores have cryptographic APIs that they can use. They can call back into Caliptra's mailbox and they can say, hey, give me a certificate. Or give me a key that you blessed and I want to use it. And I want to use it for storage, for example. Or I want to use it to encrypt DDR. It has a number of APIs, the DICE context that we talk about, PCRs, mailbox, certificate chains, and others. And, I forgot to talk about this before, but we'll mention it here. It allows you to control debug state and lock it. It's very important when you do an attestation to know the debug state. You don't want to have a chip with amazing firmware, give it to a user, but debug enable is turned on so anybody can come, connect to JTAG and take away the user's data. So that's part of the things we attest. So let's talk about the journey of Caliptra, right? Caliptra is a little bit newer than OpenTitan. In 2021, we ideated the concept. We were seeing some problems in the industry. One of the problems that we were seeing is that there was a definite move from discrete, separate roots of trust that would not withstand certain kinds of attacks to moving inside the SoCs. So we felt we really needed a standard implementation, and we were able to immediately enlist Microsoft and AMD on this journey with us. 1 year later, we brought along Nvidia. Those are the 4 companies that formed the technical advisory committee for Caliptra. We created the Caliptra core implementation. We onboarded the idea to OCP, Open Compute Platform, and to CHIPS Alliance, which is a project in Linux Foundation. 2023, we were up on GitHub. We had a community. We called Caliptra 1.0. Caliptra 1.0 had a few problems. It's not the best idea in the world to use it. Like all projects, you have to get better as you go along. So in 2024, we had Caliptra 1.1. We locked in a number of integrations. We created a CHIPS charter. We created the Caliptra charter. We created a trademark. We donated a trademark to the Linux Foundation. This is the year 2024 when Caliptra got real, right? And since then, it's been growing quite aggressively. So now we have formal trademark criteria. This year, we've released Caliptra 2.0 and 2.1. I'm not at liberty to talk for other companies, but we have over 20 integrations of Caliptra across x86 CPUs, internal products from Google, from Microsoft, I suppose, GPUs, network cards, SSDs, BMCs. It's starting to show up everywhere. What the future says for us, we understand we need one more version of Caliptra for sure, because we don't have USB support. So all of our out-of-band, flashless boot, etc., it's happening over I3C. I3C is good, but USB is faster. We are thinking about expanding into client devices. This is not an easy decision. We don't have the expertise to do that. It can really dilute the project. We're not sure about it. And we're thinking about expanding into UCIe. UCIe as one of the previous presentations alluded to, is a standard for intercommunication between chiplets. And there's a lot of thinking in the chiplet community that each individual chiplet should have a Caliptra-like separate root of trust internally. I'm not taking a position here. I'm saying this is something that we're thinking about. So that's where we are with Caliptra. That's its role. It's inside every SoC. It's the attestation and key management engine. Now, very important things we learned with Caliptra. You can do a lot of open source firmware, the mask ROM. You can do a lot of open source RTL in Verilog and everything else. You still need closed source blocks, right? You still need, we have the whole, we took it from OpenTitan, by the way. We have the whole random number conditioning and, fit into all the FIPS standards, etc., etc. You still need an entropy source. That entropy source is a closed source IP that you license from your favorite provider, but it's not an open source thing, right? Same with PHYs, same with fuses, right? We have an open source fuse controller, but we don't have open source fuse technology. We're using a number of open source tools. Verilator is great. We love it. We use it all the time, but we need a lot more of open source tools. They exist, right? People talk about Open Road and so on. But I think we need many more verification tools and synthesis tools that can point the community to credibility that the code base works and is going to meet goals, and ease of integrating them. And then, of course, every SoC is its own world, right? Booting an x86 CPU is very different from booting a TPU or a GPU. So because Caliptra kind of inserts itself at the beginning of the boot chain, even though the project is open source, we need to allow for very specific quirks and things that, closed products need to do without telling the world about it. So really what we learn is that you can define a software library like OpenSSL entirely in open source, but you cannot define the equivalent of a library. Think of Caliptra as a library that you put into your SoC entirely in open source. There's a lot of trade-offs there and a lot of things that are still closed. I think we need to work to make it less so, but there are limits here. So, and one final observation on Caliptra, this is kind of like a circle. We created Caliptra, we generated the source, we funded an ecosystem of contractors. There's a number of companies that work on Caliptra and make it better. We put a lot of work to bootstrap the community calls, GitHub, OCP, blah, blah, blah. We created a trademark. The purpose of creating a trademark is you can have all the free code in the world and everybody can modify it, but that can really dilute the project, right? So with a trademark, what you do, and Linux is a trademark as well and is managed that way, and many other open source projects. With a trademark, what you do is you establish a criteria. You only earn the trademark if the implementation is good, and that's how you try to defend the community and defend the work that they do, right? So we created it, and then we donated it to Linux Foundation. It's not good, I think, this is my personal opinion, it's not good for Google to have the trademark or Microsoft to have the trademark. We give it to Linux Foundation. But the fun part is that now we created a trademark, we donated it, and now we're applying for that trademark to be granted back to us for our own projects to use it. And that's not just, the companies that created Caliptra, but many, many other companies are going through that process. And of course, it doesn't matter what you do. In Reddit and Hacker News, people have opinions, and those opinions are sometimes a little bit unkind, sometimes not too informed, but you roll with it and you try to learn and you try to figure out what people are thinking. So these are some of the things that I wanted to convey here today, the things that we learned going down this path of open source silicon security. I'm going to pivot to OpenTitan. This one is probably going to be a little bit shorter. Some of the main messages have already been mentioned, right? So OpenTitan is actually the first. OpenTitan predates Caliptra by quite a bit. And OpenTitan can credibly call itself as the first open source security silicon chip out there ever, right? OpenTitan is different because it's a standalone chip. So it has its own storage, for example. And that's very useful. It can act as a TPM. It can hold its own firmware. You can use it for cryptographic agility. You can give it credentials. You can seal secrets. You can revoke things. You can pretty much have unlimited agility. If you look at a lot of most chips, they don't have flash inside them. And the cryptographic agility, which is the number of times you can change a secret, is limited by the number of fuses that you have. Whereas here, because you have flash, for all intent and purpose, you have infinity agility. Of course, flash is not infinite, infinitely erasable, but this is not an SSD, right? This is a thing that where secrets change once a week. So it can function as a trusted platform module, but also it is a SPI interposer. SPI is the path, by which most chips load their firmware. So it can really control what a chip downstream see, and it can be a root of recovery for a platform. So we use it as SPI interposer, as a platform root of trust, as a TPM. Because it's a standalone chip, that die can be packaged in a number of ways. So it can fit a number of different PCBs, and it can fit a number of products. So we use OpenTitan on servers, but we also use OpenTitan on laptops, and we also use OpenTitan in phones. It's the same die, different packages, different product lines, similar ideas. Secret sealing, SPI interposition. This again, I use an LLM here, and sometimes you kind of lose control of what happens, and you end up with very busy slides. But if you take a look at the traditional proprietary silicon development flow, and then you look at what OpenTitan has done, I think one of the key things that the OpenTitan project has achieved is to generate credible open source implementations and flows for most of the silicon journey. You have things that are unchangeable, right? Like chip fabrication or physical design key. Of course, we know who those are, and there's no yet path to open source there. But with OpenTitan, everything from protocols, APIs to the RISC-V CPU that OpenTitan uses, and all the other digital IPs and RTLs that we use for cryptography and random number generation and other things, all of that has become open source. The number of blocks that OpenTitan created are being reused across a wide variety of products. Caliptra is a great consumer of OpenTitan silicon, but there's a number of other consumers as well. So that has been we think, has been a very valuable contribution. The journey of OpenTitan is much longer. The vision of OpenTitan was bootstrapped in 2018. Low Risk, which is a non-for-profit, was enlisted to support OpenTitan in 2019. OpenTitan is actually a product where Google spent a lot of resourcing, and that's why because so much of the product needed to be solved, and why so many open source blocks were generated, right? So there was furious development throughout 2020 and 2021. Nuvoton was enlisted. OpenTitan is commercially available today. This chip here is a Nuvoton chip, right? Nuvoton is the first company that has manufactured and is, commercially selling OpenTitan chips. In 2023, the project was pivoted to execute primarily externally. Google has certain small amount of control, but it's primarily a low-risk control project executed by the community as a whole. The tape-outs completed in 2024, and in 2025, we committed and had power on of multiple platforms using OpenTitan. So we expect a lot of products in 2026 to be serving in the market with OpenTitan. It's a very long journey, right? You didn't see these last ones in Caliptra, right? Because the Caliptra products, the products with Caliptra are going to GA in 2027 and 2028 and so on, right? It takes a lot of time. You all know this, but it's always worth emphasizing, the very long investments that we make and the patience that we need to have for them to come to fruition. So this is the chip. It's called Earl Grey. That's a little trophy that we built for ourselves. So it's GAing in 2026 and 2027. OpenTitan, Titan is a T, so we call them with types of T's, Earl Grey, and so on. So one slide here about benefits and challenges. Again, re-emphasizing, OpenTitan has generated multiple reusable high-quality blocks. One of the challenges that I didn't talk about before, and I'm taking the opportunity to talk about it here, is, we talk about the value of a root of trust being, it's going to sign cryptographic attestations, it's going to generate keys, and so on. How do you know they're true, right? Ultimately, the value roots back to the fuses and to the unique identity that is in those fuses. And how do you put that there? That's a process called provisioning. It may have other names, but that is a process that typically is called provisioning, right? You manufacture, you have a wafer, and then you move the wafer to the next facility. That wafer becomes dies. Those dies need to be provisioned, and that's a critical step where a lot of security becomes anchored to the provisioning. So one of the contributions I'm really fond of that OpenTitan did is that it defined a very open provisioning flow with open source tools in a completely public process that is the way it's being provisioned. Those chips, those commercially available chips are being provisioned. So you can see that at GitHub, in low risks GitHub, but it spans both multiple steps in the OSAT chain, both the initial test and the final test. It uses HSMs, and it uses a provisioning service and a device registry. I just wanted to call that out. Typically when we talk about security, we put a lot of emphasis in the code and the ROM and the cryptography and so on. None of it matters if you don't have a good cryptographic identity on the chip, and this is one of the key contributions that I feel OpenTitan has done. So demo time, I don't know how we're going to show this. We're going to try. So this, I don't know, maybe we can turn on the lights. Okay. Yeah. If not, we can do it later. I mean, I didn't. You will try. You will try. Okay, let's try. Let's try. Yeah. So I'm going to tell you what you're going to see. You're going to see an OpenTitan demonstration board. It has the OpenTitan chip, of course. It has two different flash EEPROMs on it, and it has, of course, a number of serial line and UART consoles. It has a bunch of jumpers, and it has an ARM v7 microcontroller and an LCD. Oh, here we go! Yay! Okay, you can see it. Let's hope it doesn't fall. Maybe we can zoom it in while we zoom it in, right? So we're gonna go. Boop. We're booting here. It has an LCD. I don't know that you're gonna be able to see the LCD. Here you go, demo mode, OpenTitan. Well, that's me. So they sent it to me, and so you can see here. That's the OpenTitan chip right there. This is the ARM v7. These are your two EEPROMs. And then you have a bunch of different controllers, right? So what I'm going to do is I'm going to go to, let's see if I can show it to you, SPI pass-through. Can you see that? Here we go, SPI pass-through. Okay. So we're enabling secure boot here. So it's saying, what it's saying secure boot enabled, everything's fine. So we have two different EEPROMs, the one with the green light and the one without it. This is the one with the green light. This is the one without it, right? So they both carry the same code. One of them is signed, the other one isn't. One of them is a good guy, the other one is the bad guy, right? Because it's not signed. So right now, OpenTitan is enabling secure boot. It's checking that the green EEPROM is properly signed. It's allowing the ARM v7 to go from reset. So now what we're going to do is we're going to disable secure boot. So the LCD is going to tell us, oh no, you're making a mistake. Secure boot is disabled. You shouldn't do it, right? So things are fine, but now we switch to the bad guy. So this is the red one. This is the bad guy, the one below the green one. We reset. This thing is thinking, comes back. Everything is fine. Why? Because secure boot is disabled. You couldn't tell the difference. So now let's re-enable secure boot. Tamper detected. I mean, it's tamper because, you know, it's not signed. That's all that there is. So we try to reset the application, and it basically cannot come out of reset. That's why the LEDs are going back and forth. Blip, 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 blip. That's pretty much the whole thing. We can exit now. We have the other thing OpenTitan has, of course, it has a bunch of crypto. So if you're a cryptography person, you know that in AES you need to use salts and twigs, because if you don't, the same image can be figured out if you don't use a salt. So ECV is the mode without salts, and you can see the tux in there. You can see that this was a penguin before in ECV, but in CVC, of course, we use a salt for every value, so you cannot figure out that there was a penguin there. Anyway, that was the demo. I don't know, it was very simple, right? But this is a real chip, it exists. All right. I do have one or two more slides, so maybe we can, I don't, how are we doing with time? Are we good with time? One more? Okay, okay. Let's see if we can come back to this. So after the demo, you know, the role of RISC-V, well, this thing kicks off. Of course, both, choose mirror or extend. Of course, both Caliptra and OpenTitan use RISC-V CPUs. There's cryptography, there's controllers, fuse controllers, there are buses, AXI, or TLUL, all of these things, but at the heart of it, there are RISC-V CPUs. Come on, next. Right, so Caliptra uses VIR EL2 for reasons, and OpenTitan uses IBEX, both of them RISC-V. They're very uneven, right? Actually, IBEX is a much better CPU from a security perspective. It has so many more capabilities. We're trying to bring VIR up to match, or Caliptra 2.2 is going to have dual core lockstep execution. We added PMP and so on, but it doesn't have as much ECC on register files or caches as IBEX does. It is a faster CPU. That's kind of why we use it. It can achieve much higher clock frequencies, and it's much better for 3 nanometer and 2 nanometer process nodes compared to IBEX. So that's why we do, right? But there's variety and there's choice, and that's an amazing thing here with open source RISC-V CPUs. So I think it's a very simple statement to make, and I think it's a true statement to make, that RISC-V is the engine for open source silicon security, that this diversity of CPUs is a good thing. But we really need more. One of the things where we're spending a lot of, one of the things that is surprisingly expensive is control flow integrity, right? So all of the security chips, you would imagine that bad guys are going to try to glitch them and try to gain control of execution through glitch attacks. So we try to implement control flow integrity, and if you don't have native control flow integrity in the RISC-V CPU, you need to bloat your code with a lot of delays and retries and checks and redos over and over again. And bloating your code, you think, okay, that's simple. I can use libraries and ask compilers to do it. But then you end up with twice the SRAM, and then that matters, right? And then suddenly you don't fit anymore in some application. So we really, really, really need the open source community to implement control flow integrity from the RISC-V ISA in any CPU, but this one's in particular. It's starting to become a pressing problem. So to close on this presentation, I want to thank you for your time. I want to thank you for your attention. I want to thank you for looking at this silly little demo. Collaborative hardware security through open source. There's phenomenal traction here. We really like where things are going with Caliptra, OpenTitan, with RISC-V. We do need more open source tools, right? Today you go to Caliptra and you have to believe that the RTL works, and then you have to take it and then you have to work on it yourself until it works, right? But we haven't gotten to the point where I would like us to get it to, where you have a full palette of design verification tests, and you have synthesis and everything else, and you can at least see good evidence of timing and area and gate counts and so on, right? Today we're asking people to run their own flows. They will do that no matter what, but it would be great if we can have that directional signal from the open source tools themselves. On the RISC-V side, you know, there are some very good CPUs security-wise like IBEX, but we really need control flow integrity, coverage and implementation. And this is a call to action. We need open source companies here to make the community more robust, to provide quality support packages. the silicon world is funny. People really want to basically write a contract and say, it's your problem. If it doesn't work, please fix it. That's not the way open source works. But this is an opportunity for companies. And to steer trademark license applications. So that's what I had today. Thank you for your time. Thank you for the invitation. Thank you for the opportunity. And please, any questions?
Do you have any
That's a
questions?
Caliptra t-shirt because we have t-shirts too.
Hi, thank you for interesting talk. Hi. So I want to know the attestation environment. So do you offer any tool to make attestation evidence? And I want to know verifier. Can we use open source verifier software?
That's a great question. Thank you. I mean, so we're a cloud provider. I'm going to speak from a Google perspective, right? I'm going to stop talking about Caliptra and OpenTitan. We are a cloud provider, right? Every one of our customers, most of our customers don't even know what attestation is. But the ones that do know it very well. Have very specific, very specific needs. So the verification side of attestation is difficult to pin down. It's all over the place. Different customers want different things. What is amazing to me is that ultimately the measurements are all the same. The certificates are all X509. The measurements are, SHA-256 or whatever. So even though ourselves and our customers use Titan-derived measurements, the way they consume them and parse them and do their own logic is very custom and specific. So it's an example where the base capability, being open source, seems very reusable and very well defined, but how it's used on an application level by different customers is changing quite a bit.
Oh.
I wish it were different, but it isn't.
So customer depend on.
Yes.
Okay, thank you.
Thank you for the question.
Hi, thank you very much for your talk. I have a couple of questions. The first one is, do you have a booth here where we can get hands-on with the OpenTitan firmware module? Is that only for you?
I mean, I brought one. And we can I don't have a booth. It's just me.
Okay.
But okay, thank you, Champe. Thank you very much. We have a booth. It's just me. I'm going to be there. We can talk.
Okay. Yeah. The second question is, in regards to control flow integrity on RISC-V, you made a plea to for people to improve the implementation there. Don't you want to use Cherry? It's a miracle that it got implemented. It's real.
Well, okay, let's talk about Cherry, right?
Yeah.
I mean, so we have talked a lot about using Cherry specifically in this implementation, which is the root of trust implementation. Actually, my personal opinion is that that's what it's for, right? I'm not so sure, again, my opinion, that Cherry will kind of ever make it to large application cores, where people would run, a web server. But for something like a root of trust, it seems tailor-made. It seems very specific. Google has invested quite a bit in Cherry. You have to rewrite everything, right? And what we found, I didn't talk about this, right? But both of these chips, everything is done in Rust. And it's looking pretty good. It's looking pretty amazing. So we're having a little bit of a challenge to motivate people who are already in the Rust world to believe that Cherry is going to give them more, right? So when I talk about CFI in my presentation, in Rust, we have the tools that are adding the delays and doing the checks and doing things over and over again. It's actually a very simple thing to do. The problem that, which wouldn't be the case if we go with Cherry, it would be a radical rewrite. The problem that we have is that going that way is code bloat and SRAM grows a lot. That's why we're asking for instructions in RISC-V, which are architecturally defined So nobody needs to define them. We just need to put them in the CPUs. I think yours is an excellent question. I still think Cherry will succeed in one of these. But it has such a high bar, of adoption. You need to rewrite everything with fat pointers and check all the time. That it's still not the time. Thank you for the question.
Thank you. That's fascinating.
Thank you very much. ではちょっと時間になりましたので、以上で、このセッションを終わりにしたいと思います。じゃあ改めてですね、盛大な拍手で、サインを示してください。よろしくお願いします。Thank you very much, Doctor. 午前中のセッションは以上で終了です。午後はですね、2時からまたこちらで行いますので、それまで、お昼並びにですね、展示等をご覧ください。以上です。